Okay, so week 2. Last time we introduced the multiple linear regression, and we looked at the least squares estimates, and we got the expected value and the variance. But the question is that the best we can do? If I'm going to estimate beta hat, and hence the expected value of y, which is x beta hat, well, the expected value is x beta, but the estimate is x beta, can I do better? So first of all, let's recap. We've got y equals x beta plus re. And last time we got the sampling distribution of the least squares estimate, so we got beta hat. The other thing is the least squares estimate of the expected value of y. Well, remember the expected value of y is x beta. So what we could do is we could use eta hat, which is just x beta hat, is the best linear unbiased estimate of eta, which is the expected value of y. So linear means it's a linear combination of random variables. Unbiased means that it's the expected value of our eta hat will be eta. What do we mean by best? We mean that it has the smallest variance. So to do this, we're going to introduce some notation. So let's say we have a quantity where I'm going to take a linear combination of my eta. So remember, my eta is the expected value of my y. So it's a column vector with the first entry of the expected value of y1, then y2, etc. And I'm going to basically take the dot product of that. So it's a linear combination where I've got some constants, lambda 1 up to lambda n. And I'm going to basically go lambda 1 times the expected value of y1 plus lambda 2 by the expected value of y2 plus lambda 3 times the expected value of y3 all the way to dot 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 plus lambda n times the expected value of lambda yn. That thing, which is going to take my expected value of y's, which are my values that, and it's going to take a scalar vector, sorry, not scalar, a vector of scalars. I'm going to dot multiply them. That number I get out, we're going to call an estimable function. Okay? So basically, if I have any quantity that I would like to estimate, which is lambda transpose eta, that is called an estimable function. Okay, so well, why do I care about estimable functions? Well, everything we really do with linear models are estimable functions. You just have to think in terms of this lambda. So if I had a lambda that started off with a vector that zeros everywhere and 1 in the jth position, and then I multiply that by x transpose x to the minus 1 x transpose. So here's my lambda t. If I multiply that by x beta, what would be returned is beta j. So this lambda gives me beta j. So that is what I would like to estimate, and then obviously what's the best way of estimating it. Let's say I want to do a point prediction. So I want to do beta 0 plus beta 1 x plus dot 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 plus beta r xr. So I know the true model. I want to put in some values of my predictors and get a value of the y out. Well, again, that's an estimable function. My vector now would be 1, x1, x2 up to xr by x transpose x to the minus 1 x transpose. If I multiply that by x beta, I would get this out. So what we're saying is, to recap, we have this estimable function, something we would like to estimate, which is going to be, to some extent, a linear combination of our expected values of our yi's. What's the best way of doing that? And the best way of doing that is defined in the Gauss Markov theorem. So let's set it up. So first of all, we're going to assume the expected value of y is this eta. I keep going on, and because it's a linear model, it's x beta. So you take your design matrix and you have these betas. We're also going to assume that the variance of y is sigma squared I. And we're going to say, let's say I come along and I go, I am going to estimate this estimable function. So I want to estimate lambda transpose eta. And I have some sort of linear combination of the random variables, a, t, y, such that the a, t, y is chosen such that it's unbiased and linear. Well, the linear comes from the fact that it's a t y. Unbiased means the expected value of this is going to be lambda t eta. Then, I don't care what you've chosen with this, I can always beat it. And how can I always beat it? I can show that the variance of whatever this estimator is will always be greater than or equal to this version, where the way I've done my eta hat is I've used the least squares estimates. So let's think about that. You come along and say, we've got something we want to estimate from our linear model, which is going to be a linear combination of the expected value of the y's. First of all, we'll set a level playing ground. It has to be linear and it has to be unbiased. So linear is going to be a linear combination of our observed data. It's going to be unbiased, that the expected value of this is going to be equal to the estimable function we want. And you cannot beat in this using your beta hat, which is your least squares estimates. That's it. Okay? So, we're going to prove that. What I'm going to do this time is, last time when we were doing the distribution results, we went right back to basics and we did the whole proof, me writing it out. This time, we're going to go to the proof that I've given you in the handouts and we're going to look at annotating it. So this is a common thing you have to do when you're reading papers, is people have proofs, but they're not complete. What you have to do with your proof is you have to go at each step and go, how did they get from one place to the next? Now, if one place to the next is just simple algebraic manipulation, you're pretty well good to go. But if not, you should annotate it. You should make notes, almost as if you're explaining to someone how you get from one step to the next. So I've got the proof here. Now, first of all, we know that we have eta equals x beta. I'm not going to prove these first things. To some extent, you saw something very similar last week, because there we were looking at things like the expected value of beta hat. But now, to some extent, we're looking at the expected value of lambda transpose x beta hat. And you should be able to work that out. But what we're going to do is, if you look at the theorem, and you've always got to be careful, theorems never have anything in there that's unnecessary. So I didn't just say we've got any estimator. I was very specific. I said it's an unbiased linear estimator. So if it's unbiased, we're probably going to use that. So let's start by using it. So we're going to say we know that our new estimate, A transpose Y, so it's a linear combination of the observed data, is unbiased for this estimable function lambda t eta. What does that mean? That means that the expected value with this equals lambda transpose eta. Well, this is going to be A transpose the expected value of y, which is A transpose x beta by definition. So I can substitute that in, which is obviously A transpose eta. I can substitute that in and then bring this across and rearrange, and I get this. All good. But up here, I said that eta equals x beta, and we're assuming that beta is not the zero vector. So basically, I can substitute that in, and then I can, on both sides, remove the beta. So now I get this stage. And in fact, what I'm going to do now is I'm going to multiply on both sides by x transpose x to the minus 1 x transpose. On this side, I'm going 0 times this, which is just 0. On this side, I've now got x transpose x to the minus 1 x transpose, which is our p that we've used in previous lectures. So I've got this fact that A minus lambda transpose P equals 0. Okay? Doesn't mean much now, but that's the simplest form we can do. So let's start by considering the variance of our new estimator. Now, we've just here done Gary Glonick trick 1, we've added 0. How have I added 0? I've taken off lambda t eta hat plus lambda t eta hat. Then we are using the matrix form of the fact that the variance of basically x plus y equals the variance of x plus the variance of y plus 2 the covariance of x and y, where this is my x and this is my y. And that gets us to this stage. And this is a common term. What we're going to do now is we really want to show that the covariance is 0. So, because that will simplify my problem. Well, let's do that. What is the covariance? Well, I've taken this term here and just rewritten it. And then I've basically in here substituted, I've just rearranged where I've got eta hat. I've put Rx, I've rearranged and got to this point. It's just substitution and rearrangement, so I'm not going to go through the details. We've got our lambda transpose P. So basically I've just done some substitutions to simplify it. But the next stage is complicated because what I've done is I went the covariance of basically AY and BY is equal to A, the covariance of YY, B transpose. And the covariance of a random variable itself is the variance of y. So here's the variance of y. I took this constant and I went lambda t p transpose is p transpose lambda t t. P is nice and special. You'll see in the tutes, and we saw last week, that that is its own transpose. And lambda transpose transpose is lambda. So that's how I get that term. This one is just this one here. This is a nice scalar. It comes out the front, and I've got this value here. And if you look at that carefully, you'll see that that is actually 0. How we actually do that? Well, you can just substitute in there and expand it, and you will see that it's 0. I'm not going to go through the stages. I think you should have a go on your own. If you have a go and you're getting stuck with that, please feel free to get on PR to let me know, and I will put up a proof of that. But it's nice to give you something to have a go with. So the nice thing is, when we substitute in and have a look at that, what we've got is something that's 0. Just so you know, you should be able to, I say have a go. Think about this fact when you want to prove this fact. Okay? Anyway, so now I can use that fact. I can say that the variance of AT is equal to the variance plus the variance. The covariance is now 0. Now I don't know what this is, but it's a variance. So it's greater than or equal to 0. What does that mean? I'm saying the variance on this side is equal to some non-negative number plus my variance on this side. Which, if you think about it, means that it must always be greater than or equal to lambda t eta hat. And in fact, it's only going to be equal to that if this term is actually equal to 0. So it's when this is equal to 0, and the variance of that will only be equal to 0 when a equals p lambda. So there's the Gauss Markov theorem. Very, very useful. What does it mean? It means you can't beat the least squares estimates. There's the proof. You've got the proof with the stages. What I want you to think about, go away, give it a week, come back to that proof without the annotations, see if you can step through the proof and justify each step to yourself. Okay, that's it. See you next time.